Welcome to this model. In this model we are going to see about transmission control protocol. Transmission control protocol like UDP is a process to process protocol, that is program to program protocol, and therefore it like UDP it uses port numbers, and unlike UDP, TCP is a connection oriented protocol. It creates a virtual connection between two TCPs to send data. So in addition, TCP uses flow and error control mechanism at the transport level. TCP is called a connection-oriented reliable transport protocol. It adds connection-oriented and reliability features to the services of IP. And now, before we discuss the TCP in detail, now let's explain the services offered by TCP to the process at application layer. Like UDP, TCP provides process-to-process communication using port numbers, as I said earlier. Here are some of the well-known ports used by TCP. Echo's port number is 7, and where echoes receive datagram back to the sender. And port number 9 is discard. It discards any datagram that is received. And port number 11 is users. It indicates the active user. 13 is daytime. It returns the data, date and the time. And 17 is code. It returns a code of the day. And 19 is a charger. It returns a string of characters. And 20 is FTP data, which means that the file transfer protocol for data connection. And 21 is FTP control, file transfer protocol for control connection. 23 is Telnet, terminal network, and 25 is SMTP, simple mail transfer protocol, and 53 is DNS, domain name server, and 67, port number 67 is BootP, that is bootstrap protocol, and 79 is Finger, and 80 is HTTP, that is hypertext transfer protocol, and 111 is RPC, which is remote procedure call. Now, let's see the stream delivery service. TCP, unlike UDP, is a stream-oriented protocol. In UDP, a process, that is an application program, sends messages with predefined boundaries to UDP for delivery. UDP adds its own header to each of these messages and delivers them to IP for transmission. Each message from the process is called user datagram and becomes eventually one IP datagram. Neither IP nor UDP recognizes any relationship between the datagrams. TCP, on the other hand, allows the sending process to deliver data as a stream of bytes and allows the receiving process to obtain data as a stream of bytes. TCP creates an environment in which two processes seem to be connected by an imaginary tube that carries the data across the net. That is, you can see in this diagram. And this imaginary environment is depicted here, and the sending process produces or writes to the stream of bytes, and the receiving process consumes them, that is, it reads from them. Because the sending and receiving processes may not write or read data at the same speed, TCP needs buffers for storage. That you can see here. There are two buffers, sending buffer and the receiving buffer. Okay, and one for each direction. And these buffers are also necessary for flow and error control mechanism used by TCP. One way to implement a buffer is to use a circular array of 1 byte location, as you can see in this diagram, that is circular way. So for simplicity, we have shown only two buffers of 20 bytes each. Normally the buffers are hundreds or thousands of bytes depending upon the implementation. And the buffers are also shown as the same size, which is not always in the case. And here this diagram shows the movement of data in one direction. At the sending side, that is here, on the sending side, the buffer has three types of chambers. The white section contains empty chambers that can be filled by the sending process. And the gray area holds bytes that have been sent but not yet acknowledged. TCP keeps these bytes in a buffer until it receives an acknowledgement. The colored area contains bytes to be sent by the sending TCP. And TCP may be able to send only part of this colored section, and this could be due to the slowness of the receiving process or perhaps to congestion in the network. And you can also notice that after the bytes in the grain chambers are acknowledged, the chambers are recycled and available for use by the sending process. And this is why we show a circular buffer. The operation of the buffer at the receiver side is simpler. The circular buffer is divided into two areas, which are shown as white and colored, and the white area contains empty chambers to be filled by bytes received from the network, and the colored section contains received bytes that can be read by the receiving process. So when a byte is read by the receiving process, the chamber is recycled and added to the pool of the empty chambers. Although buffering handles the disparity between the speed of the producing and consuming process, we need one more step before we can send data. The IP layer as a service provider for TCP needs to send data in packets, not as a stream of bytes. At the transport layer, the TCP groups the number of bytes together into a packet called segment. Let us see in this diagram. So these are called segments. So TCP adds a header to each segment and delivers the segment to the IP layer for transmission. The segments are encapsulated in IP datagrams and transmitted. This entire operation is transparent to the receiving process. And the segments may be received out of order, lost or corrupted or resent. All these are handled by TCP with the receiving process unaware of any activities. So here you can see how the segments are created from the bytes in the buffers. You can notice that the segments are not necessarily the same size. For simplicity, we show one segment carrying 3 bytes and the other carrying 5 bytes. In reality, segments carry hundreds if not thousands of bytes. And TCP offers full duplex service in which data can flow in both directions at the same time. Each TCP then has a sending and receiving buffer, and the receiving buffer also has segments which moves in both directions. And TCP, unlike UDP, is a connection-oriented protocol, as I said earlier. When a process at site A wants to send or receive data from another process at site B, then some events occur, like the two TCPs establish a connection between them, data are exchanged in both directions, the connection is terminated. And also you can note that this is a virtual connection, not a physical connection, right? And the TCP segment is encapsulated in an IP datagram and can be sent out of order or lost or corrupted and then resent. Each may use a different path to reach the destination. There is no physical connection, and TCP creates a stream-oriented environment in which it accepts the responsibility of delivering the bytes in order to the other side. The situation is very similar to creating a bridge that spans multiple islands and passing all the bytes from one island to another in one single connection. And TCP is a reliable transport protocol. It uses acknowledgement and mechanism to check the safe and sound arrival of data. To provide services, TCP has several features that are briefly, we'll see it one by one. But the first is the numbering system. Although the TCP software keeps track of the segments being transmitted and received, there is no field for segment number value in the segment header. Instead, there are two fields called the sequence number and the acknowledgement number, and these two fields refer to the byte number and not the segment number. TCP numbers all data bytes that are transmitted in a connection. Numbering is independent in each direction. When TCP receives byte of data from a process, it stores them in the sending buffer and numbers them. The numbering doesn't necessarily start from 0. Instead, TCP generates a random number between 0 and 2 power 32 minus 1. So for the numbers of the first byte, and for example, if the random numbers happen to be 1057, if for example, and the total data to be sent are 6000 bytes. The bytes are numbered from 1057 to if you add 1057 plus 6000 you will get around 7056. So the bytes are numbered from 1057 to 7056. So byte numbering is used for flow and error control also. After the bytes have been numbered, TCP assigns a sequence number to each segment that is being sent. The sequence number for each segment is the number of first bit carried in the segment. So when a segment carries a combination of data and control information, it uses a sequence number. If the segment doesn't carry user data, it doesn't logically define a sequence number. If the field is therefore, the field will be there and the value is not valid here. However, some segments when carrying only control information need a sequence number to allow an acknowledgement from the receiver. And these segments are used for connection, establishment, termination and abortion. And each of these segments consumes one sequence number as though it is carried by one byte, but there are no actual data. If the randomly chosen or generated sequence number is x, the first data byte is numbered x plus 1. And the byte x is considered a phony byte that is used for a control segment to open a connection. Thank you.